Hi everyone, I am Jin. Today we are going to talk about the fairness in the proof of authority protocols. In this work, we explore the order manipulation attacks with related countermeasures. We only discuss the fairness in terms of consensus level rather than other scopes. Specifically, our work includes the following sections. We introduce the concept of fairness and the operating mechanism of POA logarithms. We then propose our attacks and apply them into POA implementations. We also provide the simulation and the evaluations. Firstly, we introduce the concept of fairness. In traditional centralized financial markets, market orders are executed in the centralized exchanges. The ordering plays an important role in making a profit of billions of dollars. However, such a high stake also incentivizes adversarial actors to engage in these market orders. Suppose that the share price for a company is increasing. After observing the buy order of an honest trader, the adversary creates its own buy order and gets it somehow executed before the trader in the exchange. The trader thus becomes the victim as he has to pay at a higher price than expected. The fairness in decentralized financial markets follows the same principle. The concept emerged at 2019 and developed at 2020. In the context of blockchain, the fairness refers to the transaction orders. The difference is that CeFi relies on centralized exchanges, whereas DeFi is operated on distributed blockchain platforms. As for its evolution, the paper of Flash Boys has explored the manner extractable value of POW manners. Then the notion of fairness has been formally analyzed in both Byzantine protocols and permissionless consensus protocols. Later, a lot of works follow this topic by contributing from different aspects, such as making comprehensive surveys and tutorials or trying to find vulnerabilities and different attacks. Fairness is pretty important in DeFi protocols as it is closely related to the user's asset. Breaking fairness may cause huge monetary loss or negative incentives for users because they cannot trade with a targeted price. This may also affect the consensus security, where miners put all the focus on MEV rather than mining blocks, which as a result causes the time bandit attack. We take an example that break the fairness to capture profits, which is also known as the sandwich attack. The basic principle of the attack is to launch a pair of transactions that firstly front-runs the victim transactions to buy in, which as well as pull up the price. Then the adversary backruns another transaction after the victim transaction at a higher price to sell what has just bought. Take the example of Uniswap, a decentralized exchange. An adversary first spends 10 ETH for the asset A with a current price of 0.11. Then the victim buys the asset A at the price of 0.13 due to the constant function of Uniswap. Once complete, the adversary sells all the asset A. Finally, he has earned the gap between two transactions, which is 1.7 ETH. Meanwhile, a statistic website has recorded all the miner extractable value from the day of proposing the front-running attacks. As of April 2022, the cumulative value has reached up to more than 600 millions of US dollars. Such a huge amount of money greatly damages stability of blockchain, incentivizing miners in a total opposite direction. Therefore, the fairness is very important in both DeFi and blockchain ecosystems. In the next part, we introduce the proof of authority protocols. There are two mainstream implementations called Aura and Click. Aura has been applied to many projects, including Parity, Soko, and Coin, while Click has been adopted by Ethereum Gas, GoChain, and Binance Chain. Then we dive into the details of each type of the design. We first look into the aura implementation. Sellers in aura take turns to become the leader who can propose blocks. The seller rotation is relevant to clock time, step duration, and committee size. Each seller has the same possibility of being the leader. For instance, we assume that there are totally 5 sellers in the committee. At some time, the step is calculated to be 11. Then the result of its rotation function is 1, which means the first seller becomes the leader and he can start to produce the block. Then we look into how click operates. The committee includes 3 types of sellers, namely the in-turn seller, the edge-turn seller, and the out-of-turn seller. Each node in the committee takes turns to change their roles. For instance, at the time T1, A3 is the in-turn seller while A4 and A5 are the edge-turn sellers. At the time T2, A4 becomes the in-turn seller and A5 and A6 became the edge-turn sellers. The differences among the 3 types of sellers are the ability to produce blocks. The out-of-turn seller cannot produce any blocks, they only receive the blocks from others. Both in-turn and edge-turn sellers can produce blocks, and they form a parallel block producing mechanism as the feature of the POA protocols. As for the differences, the in-turn seller can produce a first priority block, while the edge-turn sellers produce the secondary priority blocks. The first priority means other members will obtain this proposal at the highest priority. If there was no first priority block, members will obtain the secondary priority blocks according to their appearance time. The mechanism is designed in case of the in-turn seller getting fails. Also, we highlight their intrinsic differences on code bases. The receiver can identify the level of priority based on its difficulty field. Every first priority block embeds the security of 2, while the secondary with 1 and other to be 0. This field is very important because every block acceptation has to verify this field. But here is a question: how to identify the block priority generated by different block producers if they all produce blocks? The answer is to add a delay time. The first priority block not only has a difficulty of 2, but also has a shorter delay time. Members can receive the proposal with an advantage during the block propagation. Other edge-turn sellers do not have better strategies under such a design. After the overview of POA protocols, we look into how a transaction is executed in the blockchain system. Firstly, a seller called the node A receives the transactions from distributed clients and collects them in his transaction pool. Then he packs the transactions into a block and broadcasts it into the peer nodes. When reaching the consistency among distributed nodes according to consensus algorithms, the block is deemed to be confirmed. Following the same procedure, the transactions are ordered in a linear sequence from the transaction 1 to transaction 9 in 3 connected blocks. Our work includes 2 types of attacks, namely the type 1 attack and the type 2 attack. The type 1 attack is to break the transaction level fairness. Specifically, we assume that the node A is a profitable seller who is rationally pursuing profits. He will launch a front-running attack in the transaction pool by manipulating the transaction orders. This is a general attack that can be applied in many consensus algorithms. We implement this attack on the POA instances. The type 2 attack is to break the block level fairness. In this attack, a profitable seller will cut in lines to occupy an advantageous position during the seller rotation procedures. A front-running position of the seller will break the fairness of blocks because the profitable seller can produce more blocks than others. For instance, the node B has taken the seat of node A, and he can accordingly insert profitable transactions in his block. As a comparison, we can see the differences between type 1 and type 2 attacks. Type 1 targets at a transaction ordering by manipulating transaction orders in the transaction pool. It results in a larger amount of damage called the MEV. Type 2 breaks the legal order of election turn by attacking the node rotation procedures, which indirectly reorders the received transactions. We showed implementation details of our attacks. Firstly, we will apply the type 1 attack to click. The attack targets to the local transaction pool to manipulate the order of transactions. The attack point 1 is shown in the red color. Then we will apply the type 1 attack to aura, which is also shown in the red color. We can observe that the type 1 attack happens at the same point for both aura and click. As for the type 2 attack, the profitable adversary aims to front-run the seat in front of him for unfair chances of block producing. In this type of attack, a precondition is that the intern sealer cannot normally work due to the reasons such as network congestion or being attacked. Under such a situation, edge turn sealers came to the center. They sent the blocks with the difficulty with 1, which are the secondary priority blocks, but they are legal blocks. We first apply the attack to aura implementation. As in the figure, sealer 2 is the in-turn sealer, while all others are the out-of-turn sealer. In this case, the type 2 attack cannot apply to this attack because other out-of-turn sealers cannot generate blocks. The parallel block producing mechanism only exists in the click. Similarly, we apply the attack to the click implementation. Here, a leading sealer, sealer 3, has failed, but both sealer 4 and sealer 5 are edge turn sealers that can propose blocks. But how to ensure that the sealer 5 can front-run the sealer 4? This is a key point of this attack. To achieve it, an adversary, namely the sealer 5, intentionally shortens the delay time so that this block can arrive at other peers faster than the block proposed by sealer 4. Then we set a series of experiments to launch the proposed attack. We have 8 mining nodes to synchronize transactions and block data, and they can merge transactions into the block. There is only one boot node used for the node discovery. We suppose that there is one profitable edge turn sealer in the system to pursue profits. The transactions are generated and broadcast at a constant rate of 10 TPS with a fixed period for 40 minutes. We present the experimental results of the attack simulations. The right figure shows the results of the type 1 attack. Experimental 1 shows the original order of the transaction list, transaction 1, transaction 2, transaction 3, and transaction 4. Experiments 2 to 6 show the results under our attacks. We can observe that the transaction S, which is a profitable transaction, can be rearranged in any order of the transaction list. This type of attack is feasible at both aura and click implementations, which indicate that the type 1 attack is a general attack in POA protocols. Here are the results of the type 2 attacks. We summarize from 2 aspects. Firstly, for aura, the results of the successful front-running blocks remain 0. This indicates that the type 2 attack cannot perform effectively in aura. For click, the attack is effective and has significant damage. The attack affects both the number of victim transactions and victim blocks in a positive relation. Furthermore, we can also see the trend and the success rate of Type 2 attack along with the changes of the committee size, implementation tabs, and the number of blocks. As for impacts on security properties, we can see that our attack do not change the essential consistency and the levelness properties. Instead, our attack breaks the fairness of existing protocols. As for the competitive attacking strategies, both clone attack and the 51 attack destroy the consistency and levelness, whereas the sandwich attack remains them but breaks the fairness. Our attacks will cause a monetary loss for both users and other sailors. A single user may buy the token at a higher price, and as a result, they spend more costs than ever before. As for other faithfully acting sailors, they can only earn less incomes because they lose the chance of proposing blocks in their normal turn. Furthermore, we also provide some countermeasures for both the Type 1 attack and Type 2 attack. For the Type 1 attack, two ways are proposed. The first way is to have the transaction value against the miners using zero-knowledge proof. The second method is to rely on hardware-assisted TE to ensure the integrity of program execution. For the Type 2 attack, one way is to verify the identities of the edge turn sailors, which needs to be properly matched the previous blocks. Another way is to have a rotation scheme, making the turns unpredictable. At last, we conclude this work from the following aspects. We reveal a large scope of proof of authority protocols and select 10 of them for the detailed investigation. We then study the notion of fairness in the context of blockchain and explore the unfairness issue existing in POA protocols. Based on that, we follow and propose two types of attacks separately targeting the transaction level and the block level. We apply the attacks to the POA implementations